Hello, this video is a guide to how Linux stores usernames and passwords. This will include instructions on how you can perform password recovery on a Linux system using Raspberry Pi as an example, and we're going to show how you can reset the password without knowing it in the first place. This video is also an introduction for a video I plan to make in the future, which will show how hackers try and crack the system passwords. In my earlier video, I explained about the importance of passwords. In this video, I'm going to look at these in a bit more depth on how they are stored on the Linux system. And then the future video will show some of the vulnerabilities of how they are stored. I'm going to start with a little history, just because this will make the explanation both a little simpler and it'll explain the reason that the password field is configured the way it is. Linux is based on the Unix operating system. Back in the 1980s and earlier, as my children would say, the olden days, the password information was stored in the password file. The file is often known as the etc password or passwd file, and it's available to anybody on the local system to be able to read. This has some security implications which I'll explain about later. The file is plain text, so anybody can view it, although you need to be root to be able to edit it. I'll just go through the fields here. The top line shows the names of the fields, and I'm going to show a working example here. So the first field is the username. Typically this represents the real name of the user, or it may refer to a system account such as root, which is the admin account. The next field is the password. If we put the plain text password here, then it would be readable for anybody, which is obviously bad. Instead, this is a hash value of the password, and this particular example is an MD5 hash of the word password. I'll explain hashing and its vulnerabilities later in the video. On newer systems, the password is moved to the shadow file, and instead you just get an X in this position in the password file. This adds an extra level of security, and I'll explain all about why this came about. You may also see an asterisk or an exclamation mark, which indicate that the account will not accept logins, although typically that will be in the shadow file as well. But if the password field is blank, then a user can log in without needing to supply a password, which is usually a bad idea, but useful for password recovery, as I'll show later. Next are the user ID and group ID. The UID is a unique number for this particular user, and the GID is the ID of the default group for this user. On modern systems, there'll normally be a group name which is the same as a username, and these are created automatically when you use the add user command. And the UID and GID will be the same. For user accounts, the UID and GID typically start at 1000. The lower numbers are reserved for the special accounts. Note here that I'm showing the line wrap into the next line. This would actually all be on a single line. And the next field is known as the GCOS field. I'll refer to above as the user info field. And this is where you include information about the user, such as their name, possibly their phone number or other information. Next is the home directory. Normally each user has their own home directory, which is in the /home directory and is named the same as their username. And the final field is the shell. This is the command line user interface that you get when logging in through a text terminal or using a remote terminal such as SSH. For most users this will be the bash shell, which is /bin/bash. For system accounts that do not allow logins, then this is normally set to /usr/sbin/no-login, which will not allow interactive shell sessions. As I mentioned previously, this is the password field, and you can't put the plain text password in that field, as it obviously everyone then would be able to read it and know what your password was. So we need a way that the computer can know if you've entered the correct password, but so that anyone else that looks at it can't tell what your password is. And this is where a hashing algorithm comes in. I'm going to show this using MD5. This was used for passwords in the past, but the algorithms used today are usually a lot more secure. MD5 is still quite widely used for other purposes. MD5 stands for the Message Digest algorithm, and MD5 is one implementation. It's not necessarily the 5th version, as the name might suggest, because some of the version numbers were never actually used. I'm going to walk through how the MD5 hashing algorithm works. We start with the password here, and here I've used the word password. Obviously you'd use a more secure password than this. This is processed by the MD5 hashing algorithm, and this results in a 32 character long string. Note that this is actually a 16-bit hexadecimal number, but represented as text. The important thing is the direction of the arrows in the diagram. So note that whilst you can go from the password and get the output, it is not possible to reverse this and get back to the original password if you have the hashed output. If that was possible, it would break the whole concept of the password hash and it would render it unsafe. I won't go into the details of how the hashing algorithm works. This diagram gives an approximation. The important thing is not to be able to go in the reverse direction. Now, this is one of the key differences between encryption, which can be reversed, versus hashing, which can't. Obviously for encryption you do need to know the key and the algorithm to be able to reverse it, but even if you know how the algorithm works for a hashing algorithm, you can't reverse it. So only the output of the hash is ever saved on the computer, and after storing it in the password file, the computer cannot find out what your original password was. As it cannot be reversed, the way the computer is able to validate the password is that when you enter your password, it performs the same hash algorithm against it and checks to see if it matches the saved password hash. Now, MD5 is now considered to be broken. It's not that it's possible to go in the reverse direction, but it may be possible to create a collision instead, which is another string that gives the same MD5 hash value. So whilst you might not be able to get back to the original password, what you might be able to do is think of another password that would give you the same value. It's still quite complicated, but it is theoretically possible. Even before the algorithm was broken, there were other ways of defeating the hashing algorithm method of creating passwords, and some of these are still possible with some of the other algorithms. I've discussed some of these in my earlier video where I discussed ways of guessing the password using dictionary attacks and brute force attacks, and these both rely on trying different combinations of possible passwords and just passing them through the same hashing algorithm. An additional risk with a hashing algorithm such as MD5 is that it's possible to create rainbow tables. These are often used by online MD5 decryption tools, and you're able to have a go at one of those if you want. They're a form of brute force attack, but instead of needing to rerun the algorithm for every permutation, they're run once and computed into a large table, and then that table can be efficiently searched afterwards. A way of defeating this is by adding a salt to the password. And this salt is a known string, and it's normally added to the start of the password before the hashing, and it prevents the tables being used. So as long as different salts are used for different systems, it effectively makes it unfeasible to be able to create sufficient rainbow tables to be able to break it using this method. Here's a few of the hashing algorithms that are used for Linux passwords. And when you look at the password string that is generated, they start with a few characters, and these are telling you the algorithm that's used so that the system knows what algorithm to apply to your password. And this choice is normally made by your distribution, but if you have a choice of hashing algorithm, then I would recommend the two bottom ones, either the SHA-512 or YesCrypt. And those are the ones that are commonly used on most Linux systems. So if you look at this, it's showing you that MD5, the first few letters of the password entry would say $1, and for YesCrypt it's $Y. And you'll be able to see those if you look in your password file, or technically your shadow file. We'll come on to that in a minute. So although the new hashing algorithms are much safer, they've still got risk of dictionary or brute force attacks, especially if the user chooses a poor password. And this is why the password is no longer stored in the etc password file. Instead, it's moved into a different file called /et/shadow, which is a bit of a compromise, because the ideal solution would be to make the etc password file so that only the admin root user could read it, and then you can just have it all in one file. However, that would have broken other programs which were relying on being able to access the safer information that's contained in that file. So the solution they came up with was to remove the password from etc passwd file and instead store that into the file /etc/shadow. And if you look at the passwd file, the password field has been replaced by an X, lowercase x character, which tells the system to look at the shadow file instead of the password being in the password file. This shows the format of the shadow file, and the username is the same as the password file, and then the password, which is stored in the second field, and again this is the hashed password field. They also added other fields which store details about when the password was last changed, the minimum and maximum days that the password is valid for, the number of days to warn before forcing a password change, the number of days after it's inactive before it gets disabled, and finally when the account expires. As promised, I'm now going to show how you can use what we've just learnt about the password and shadow files if you find yourself locked out of a Linux system. This is based on using a Raspberry Pi. It'll also work with other Linux systems, but in that case you'll either need to boot into a system mode, or what's known as a recovery mode, or perhaps use a live boot disk to be able to access the system and then onto the drives. Alternatively, you could always remove the drives from the computer, but that's getting a bit more hands-on physically with a computer compared to the Raspberry Pi, where it's just a case of pulling out your micro SD card. Here I am. I've got a Raspberry Pi system and I've set a very long password and I don't know what the password is. So effectively I'm logged in. I can try guessing a password. I know that the user is Pixel Server, but if I try the password, hit enter, I'll click log in. Incorrect password, please try again. And without knowing that password, obviously I can't get on the system. However, the one thing about Linux systems, in fact most computer systems, if you can physically access the drive and the data is not encrypted, then there's ways of resetting the password. And so that's what we're going to do. I'm going to shut this computer down and then remove the SD card, bring that into another computer and show you how I can basically remove the password. So I've taken the SD card out of the Raspberry Pi. I'm going to pop this onto my Linux computer here. So you need to put this into a computer that's able to read ext4 file systems, which is what is used by Linux. So as you can see, the elements is my external drive, so we can ignore that. We've got two drives appeared, one's called boot and the other's called rootfs. Boot is the FAT32 file system that holds the boot information, but the rootfs is the entire root file system on the Raspberry Pi. So this is the one we're interested in. And we're going to click on that, and we're going to go into etc, and the password file and the shadow files are both in here. There we are, we've got the password and the shadow files. You'll see that we're actually unable to edit this at the moment. We don't have permissions to view that. So that's what this red circle is. So we're going to have to do this as root. What we can do is launch terminal, and then we'll change to that. So it's mounted into media, then under my own username, and then it's called rootfs. And it's then in the etc, and it's the shadow. So we have to use sudo to edit this as root, and we can edit. I'll use the vi editor. You could use nano, or you could use any other editor you want. And now I'm going to go through this to find the password of the user that I'm wanting to get on. So you can see, so it's pixel server is the username, and as I said, the $y$ indicates that this is a YesCrypt, a hash value, and basically we can just remove that entire thing up to the next colon. And now this has got no password, and that means you can just log in without any password. We'll save that. I'm going to just run sync. That's just going to make sure that it's written to the SD card and it's not just kept in a buffer anywhere. And then I can switch back to the window. We can just eject that. Busy because I'm still in it. So just eject that now. It said it can now be safely removed, so I'll pop that out, pop that back into the Raspberry Pi, and we'll see if that's worked. So I've taken that SD card after I've modified the shadow file and put that back into the Raspberry Pi and booted up. Now, without a password in, find a lot of the default network services won't allow you to log in anyway. They'll only let you log in if there is actually a password set. So in this case, I'm actually physically on the Raspberry Pi here. I've got a console connected directly to the HDMI output, so I can log in directly here. The username's Pixel Server. Just leave password blank and click login, and as you can see, it's taking me straight in. There's no password needed, and that's thanks to editing that password file. Very important that you change that password straight away, so we can just use the passwd command. Now I'm going to use a really simple password here, just going to use the word password. Obviously you wouldn't use that, but this will now allow me to have a look at that shadow file. That we edited earlier, and you'll see that this has put that password in. So this is the YesCrypt version of the word password. And that's how you can recover a server where you've logged and lost the password. The important thing really is that it's the physical security that prevents you doing this. If you can physically access a device then you're going to be able to get to the data unless it's all encrypted. And that's the only way you can really protect the data, if somebody can physically get hold of the disks that it's stored on. So obviously I'm going to change this password now to a nice secure one. Hopefully this video has given you an insight into how the Linux password and shadow files work. Remember, the MD5 example used was only for example purposes. There are much better hash algorithms available today. If you learned something new from this video, please give it a thumbs up. If you've not already subscribed, please do so. Click the notification icon to get notified when I create my next video. Thanks for watching, and I look forward to seeing you on a future video.